Welcome everyone. My name is Mohammad Abul Bashar. Today I would like to talk about our paper Deep Learning for Bias Detection from Inception to Deployment. Unfortunately, unconscious bias has become increasingly pervasive. Though an increased awareness of unconscious bias can benefit, it is not a systematic and consistent solution. Several studies, including McKinsey, found that if an organization support diversity and inclusion, it performs better than other organizations. Therefore, to create a more inclusive and diverse work environment, organizations are actively looking for solutions that can eliminate unconscious bias in various activities. Though there are several analytics products that consider employee demographics, pay parity, and customized training, there is a lack of solution that can tackle unconscious bias in contents generated within an enterprise. An enterprise-generated contents can include unconscious bias in several forms. For example, it can be through the incorrect use of pronouns in job description. It can be through toxic message and bullying in enterprise platforms, or it can be through the reference of body shape in e-commerce product, or stereotyping of a user in product description, or maybe there is a assumption of gender of a potential investor in stock market report. In this research, we propose a deep learning model to automatically identify bias in enterprise contents. The model is trained with manually labeled instances. It uses progressive transfer learning through language model to improve accuracy. The model is thoroughly evaluated with independent datasets to make sure its generalization to application. Then the model is integrated with enterprise applications and deployed in the real world. This paper makes three main contributions. It proposes a comprehensive bias detection model that can detect four types of bias in text data. It uses progressive transfer learning that allows to train a small model using a small set of label data while maintaining a high accuracy. It deploys the model in the real-world applications. Bias detection or identification can be defined as a function that map a given instance X to the corresponding class label CK. It essentially estimates the conditional probability of CK given X. The joint probability of CK and X can be estimated as the conditional probability of CK given X multiplied by the prior probability of X. The prior probability of X can be seen as a regularizer for uncertainty associated with the joint probability of CK and X. As P of X or prior probability do not depend on the class distribution CK, this means this prior probability can be learned from unlabeled data. A discriminative model such as AusDM learns to classify an instance X into class CK by approximating the conditional probability P of CK given X using a list of parameters theta. However, if the available label instances are limited, then the parameter set theta can overfit the label instances. An alternative solution can be a model can learn the prior probability P of X using one or more large unlabeled datasets and then use that prior probability to regularize the parameter set theta in the approximating model. Our prior research showed that if we estimate the prior probability P of X using a sequence of unlabeled datasets and then use that prior probability to regularize the conditional probability, we can improve the estimation of joint probability of X and CK, especially when the labeled dataset is small. In this study, we use a similar technique to improve the prediction accuracy utilizing unlabeled datasets. Unlike common transfer learning, where prior probability P of X is learned once from a large unlabeled dataset, we propose to progressively learn prior probability P of X using a sequence of unlabeled datasets. This allows us to use relatively a small number of parameters in our estimation model for P of X. A smaller model means we will need less number of label instances for training or setting the smaller number of parameters in the model, and it will take less time for making inferences when we deploy the model. Because we are progressively learning P of X from a sequence of datasets, we can decide which dataset to emphasize during our training process. This will allow us to emphasize more relevant dataset for our bias detection task. As shown in figure 1, we estimate P of X using an LSTM-based neural network language model trained on unlabeled dataset. We first pre-train a language model using Wikipedia, then fine-tune the model with a large unlabeled dataset related with various types of enterprise content. Then we use the estimated P of X for regularizing the classification model. In this phase, a fully connected layer followed by softmax layer is added at the end of the language model. Then the model is trained with labeled bias data from the enterprise contents. We evaluated our model using two independent datasets. One is iShield.ai dataset, another is SSW dataset. iShield.ai dataset has around 57,000 instances. On the other hand, SSW dataset has only 1100 instances. iShield.ai dataset has imbalanced distribution of classes. On the other hand, SSW dataset has a very balanced distribution of classes. Table 1 shows some of the examples from SSW dataset. Table 2 shows experimental results from SSW dataset. We saw that SSW is a very small dataset, and our LSTM model performs significantly better than all the 10 baseline models in this dataset. Beside LSTM-W, we used two other transfer learning based models. They are CNN-W and LSTM-W. They use word embedding based transfer learning, and they become second and third best baseline model in this experiment. From this table, we can conjecture that transfer learning based model can produce better outcome than other models, and that language based transfer learning, for example LSTM-LM, perform better than word embedding based transfer learning, for example CNN-W and LSTM-W. It is interesting to see that CNN-W outperforms CNN and LSTM-W outperforms LSTM. CNN-W and CNN use same architecture, and LSTM-W and LSTM use same architecture. However, LSTM-W and CNN-W use pre-trained word vector. Therefore, they can produce better result. This further emphasizes that if we use transfer learning, we can get better result, especially when the dataset is small. Traditional model, for example, random forest, decision tree, Gaussian net bias, and k-nearest neighbor, they do not utilize transfer learning. They solely rely on labeled dataset. Therefore, their performance is lower compared with transfer learning based model when the dataset is small. Accuracy, area under curve, that is AUC, and Cohen-Kappa scores, that is CKS, are three important measures for understanding the overall significance of a classification model. Our LSTM-LM gives the best accuracy, area under curve, and Cohen-Kappa score results. Cohen-Kappa score indicates the reliability between the prediction made by a model and the ground truth. All the three transfer learning based models, that is LSTM-LM, LSTM-W, and CNN-W, have high Cohen-Kappa score. However, our LSTM-LM has better accuracy and area under curve compared with other transfer learning based models. We saw that iShield.ai dataset has imbalanced class distribution. Weighted average is more reliable evaluation for imbalanced dataset, as it considers the proportion for each class in the dataset. Overall, LSTM-LM gives us the best result because it gives us best weighted averaged, precision, recall, and F1 score. Even though SBM, CNLW, and LSTM-W have the same weighted average precision value as LSTM-W, but their recall and F1 score are very low compared with LSTM-W. A balance in both recall and precision is needed, because if the recall is not high enough, then we will not be able to detect many bias in the text. On the other hand, if the precision is not high enough, we will end up with many false positives. A higher F1 score means both the precision and recall is high. LSTM-LM gives us best F1 score for weighted average and macro average. This means our LSTM-LM is a best suitable model for detecting bias in enterprise contents. Our backend system is deployed on Amazon Web Services, that is AWS, and our frontend system comes in 4 different flavors. They are DOST, Chrome plugin, content screener, and application programming interface. DOST is a bot that can be configured to detect bias on enterprise communication platforms such as Slack and Microsoft Teams. Right now, this bot is available on Slack store. Content Screener is a web application that allows for checking bias in text contents before those texts get published. Then we have Chrome plugin and API. Chrome plugin can be configured with Chrome browser for screening text contents for bias detection, and the API can be integrated with the enterprise system. Thank you for joining my presentation. Please let me know if you have any questions.